Well, first of all, thank you so much, Henry and Debbie and Kevin, giving me the opportunity to share my CCAT funded project today. It has been a really exciting project. So the title is Modeling Drivers' Route Choices and the Route Compliance when interacting with an eco-routing navigation system. So basically, Henry just gave a long introduction. Sounds very impressive, but you could imagine that's basically written by myself. So first, I want to basically introduce the team members. So I'm the PI on this project, and Dr. Jim Sayre served as the co-PI. And here's the list of names. The people who have actually done the real technical work, like Dylan Funkhauser was leading the data reduction with our intelligence students, Amtre Isam Bazina, Will Wang, and Bo Yu was the lead people doing the statistical analysis. And we also have Ziyang Huajian and Ziyang Chen Hebo, who actually helped with the GPS data correction. So with all these wonderful team members doing the real work, so basically my part of the role in this project is putting all the pieces together, and I get the opportunity to talk to everybody about this study. So also, when I start, I also want to mention, so I see a lot of familiar faces and new friends, and welcome and thank you for spending time with us today. So there might be slight chances that my internet at my house may not work perfectly as we would expect. So please be patient with me. And also at the same time, it's a freestyle. If you have any questions at any time, feel free to stop me and ask. So here's the contents of my talk today. I will talk a little bit about the background and methodology part, the results, and of course, the conclusions. So introduction. So we are not just doing the research related to safety. We are also doing research related to all kinds of stuff, including the fuel consumption and mobility. So here is the one study specifically related to the fuel consumption. So based on the EPA data, so in the year 2017, the total US greenhouse gas emission, about 1/3 of that is coming from our transportation system. Now, among all the transportation system part, is about 41% actually coming from the passenger cars. So it is very reasonable to imagine if we can improve our passenger car fuel consumption efficiency, that can totally significantly change our gas emission pollution problem. So here comes one potential solution, which is the eco-routing navigation system, which is defined as optimize the routes based on the most energy efficient. So it is different from the fastest route or shortest route. So it's basically most fuel consumption efficient. So if we imagine all of our passenger car drivers are going to adapt to the eco-routing navigation system, so it will greatly change our fuel consumption future. So having said that, we know eco-routing navigation system is a very promising solution to improve our fuel consumption efficiency. However, we do need the drivers to comply with these suggestions. For example, sometimes when we design some ADAS systems, some people choose really loving it, but some drivers say, hey, I don't really trust it. So there is always going to be decision making. So drivers are going to react differently. So it is important to develop some models to understand how drivers are making decisions. So here's the two main objectives of the study that I'm going to talk today. The first is to investigate and predict preferred routes that driver is going to pick from a list of recommendations. So then we're going to develop some prediction models to see what kind of factors, scenarios that drivers making decisions. So the methodology part is really a exciting part. So we have, today I will talk about a total of 5 key parts. The first one is the cell phone-based eco-routing navigation app development. So I want to mention that this part of the work was not conducted by people. So because was in a collaboration with the Oregon National Lab that was from a previous study sponsored by the Department of Energy that led by Professor Wei Pim. We had the collaboration with the Oregon lab working on this system. So this system was also leveraged in this particular study. So, but I will provide you a background of the development of the cell phone-based app. So then I will talk about the data collection, participants recruitment, data reduction, and also the very exciting part is the how we all know that the GPS data collected by cell phone sometimes can be crazy, not very reliable for for a lot of time. So what kind of the models, algorithms we used here at UFM that to basically correct those drifting GPS data. So then I will talk about the statistical analysis as well, which is the mixed model analysis to basically interpret drivers' route choices and their compliance. So then I will talk about our algorithms by using the multi-label random forest algorithm to predict drivers' route choice behavior. I want to mention that this is an ongoing project. So today I'm going to share our data reduction and analysis results from the phase 1 analysis. So currently we're still conducting the phase 2, which I will briefly mention at the end of this the talk. So a brief introduction about the cell phone app on the eco-routing application development, as I mentioned. So this was in a collaboration with Oregon National Lab. So they developed this cell phone-based application. So there are several channels of data being collected by using this app. The first of all, we collect basic trip information prior to each starting of a trip. So before people start moving their car, they need to fill in a survey. So the survey question including what is the trip purpose, what kind of a car models they are driving, and I will talk a little bit more later, giving examples. So then this app will be providing 1, 2, 3 routes choices. Most of the time it's 3 routes choices to drivers, basically representing the eco-routing choice, the fastest route choice. The third one is called a balanced, which is between those two. So then also this app is providing turn-by-turn guidance for a selected routes. It's just like our GPS navigation. So then basically the information of the drivers actually driving is also recorded, which for the further analysis. So here's, I just want to give you a brief demo of how this app works. So this is the interface of the survey. So when the driver participant is starting a trip, so he's asked to basically fill in a survey. The survey asking what is the purpose of the trip. So then let's say if you select it's a work purpose trip, so then you will ask you, when did you decide to take this trip? How many passengers are coming along with you? How flexible is your travel time? And other, as well as the car models. So all these relevant information captured by this survey were coming from previous route choice model survey questions. So then you can see from these picture here. So for this route, typically drivers will be provided 3 routes. So route 1, route 2, route 3, for each of the route choices, it has information about the total distance calculated for you, and the total fuel consumption, and the total traveling time. So also you may have noticed that these 3 routes may not be exactly mutually exclusive by like putting tags on them. So for example, route 1, you can say it is the shortest. It is not necessarily shortest, but it is the fastest route with the minimum travel time estimate is 27 minutes, and also it is most fuel consumption efficient. So that's why later on we use the multimodal random forest tree algorithm to deal with this problem. So then once you filled out these questions, then basically you need to enter your location to get access to the recommended route. So basically you say, okay, I'm going from my home current position to the, let's say, Detroit airport. So then you will calculate in the background, so what is the total traveling distance, what is the fuel consumption, what is the traveling time. So then, let's say you select route 1. So basically, you will give you turn-by-turn navigation instructions, as well as the mapping instructions as well. So then basically, I just this part of the work was conducted by Oregon National Lab. So, but I do want to basically give you a very brief background of how those were calculated, the MPG fuel consumption. So basically, those 3 routes, were estimated based on 3 main factors. First of all, the average speed, the traffic information, which is the traffic volume, and what kind of car models you are using for that particular trip. So basically, the traffic information were estimated by using the MapQuest API, while the average velocity and the car model, then you mapping the MPG on different under different traffic density condition, traffic volume condition. Those values are actually available on the U.S. Environmental Protection Agency website. So here's the calculation equation that how you can calculate the global MPG for a certain trip. So based on, you basically just divide the whole trip into different traffic volume conditions by leveraging the result from MapQuest. Then you basically calculate what is the average speed for that segment, what is the distance. So then once, what is the data collection and analysis part? Basically, we leverage the participant pool from the Armtree's and number collected vehicle test environment, which is called ACVTE program. So we approach to them saying, hey, here's the study that funded by CCAT and the DOT. We are interested in collecting your route choice situation. So we totally have 43 participants enrolled in this specific study. So each of the participants were given a cell phone, which already had the eco routing and navigation app installed on that. So everybody was having the cell phone for 2 weeks. So they were expected to record data for at least 20 trips over the 2-week period. And they were compensated for $100 for their time. Of course, the we got the approval, the RB approval. So then, totally from the 43 drivers, we collected information from 1,024 trips. But of those 1,024 trips, we have to define what is called a valid trip. So valid trip was defined as that the drivers has to complete the survey, so has the completed survey information, as well as a fairly complete GPS data set. So that being said, because we understand that cell phone-based GPS sometimes they can get lost and missing data. So by doing the first initial data reduction, so we had a total of 738 valid trips were identified from the original 1,000 trips. So those 738 valid trips, we basically from the 39 participants, which is we have 22 female drivers, 17 male drivers. So their age is really wide, from 20 to 72 years old, with the mean age of 47 years old. So here's the map. Actually, because by doing this data analysis, we are facing two sets of data. One is called the recommended routes. So for the recommended route, because of the limitation of the app, we only have the information turn by turn information. We don't really have the GPS information. So that means that we have to employ a mix of manual and automatic data reduction that was conducted by a group of students from my lab, that they used a software called OVTOL Maps. So basically by using for each trip, there is a turn by turn information. So they had to hand pin down the node at each turning position, so that can automatically later on generate the tracing map for the whole recommended routes. So for example, the blue route is basically coming from one recommended routes that the tracing map was generated by using the OVTOL Maps software. So then we look at so the second GPS data we're looking at is the real driving data. So because we're interested, once you provide a recommended routes and also you picked one of the from the 3 or 2 choices, are you really following the selected one? So here's the one example of the real driving case that you can see the majority of this route that they are identical with the recommended routes. However, the circle part, you can see there is a slight differences. So that basically, we had to calculate two types of outputs. One is a binary saying that whether the driver follow the recommended route, yes or no. Then we also calculate the percentage of overlap of their real driving data versus the recommended routes. So here's another example about, so the blue dots is basically the GPS are from the recommended routes, while these orange GPS information is from the real driving data. You can see there is overlap after this data point. However, before this data point, there is very different. So we, and also when we look at the real driving data that collected by the cell phone, we have found a lot of a bigger problem of data cleaning. So basically, we know that cell phone collected GPS data, they have drifting problems all over the routes. So we basically did 4 steps to basically clean the real driving GPS data. First, we did the correct GPS drift by basically removing the drifting points and replacing them with the real on the right track road GPS data. So then the second step is that we did a reverse geocoding by we know the correct lateral, longitudinal, and lat information. Then we need to identify the location, which is the name of the road. Then the third step is basically we needed to identify the overlap of the real driving versus the recommended routes. Then we need to calculate the percentage of the overlap. So all these 4 steps were conducted using Google API and Python coding. So I want to talk a little bit about all those 4 steps. The first one is called the GPS signal drift issues. So as you can see from the map here, so the blue dots are the correct ones. They are actually mapping to the real driving road, while you can see the red GPS data actually is drifting, which is not correct ones. So we have to basically removing those by replacing those incorrect GPS data with the correct on-road GPS data. What we did is that we used the function Google Maps API, the function called snap to the roads function. So we did multiple steps. For each step, we need to input 100 GPS data points at each step. So then the input is the 100 GPS data from what we collected from the cell phone. Then the output will basically returns the 100 new and corrected GPS data points by removing all those red drifting points. So that's the first step. So then you have to do multiple steps. So the second step is basically you input another 100 GPS data points, and then you will get another set of 100 corrected ones. Then you basically do the same thing for the following remaining of the trips. So one thing I want to mention that when you do this, you basically need to make sure that all those so the two two continuous steps, you need to make sure there is overlapping of the GPS data. So make sure that is making sure it's on the same road segments. So that is the first part, is correcting the drifting GPS data. So then the second part is basically mapping location, identify your position, which is we need the road segments here. So the function we used here is also from the Google API called the reverse geocoding function. So you basically input all these long information, so then you will be getting the address, for example, 2901 Baxter Road, which is the location address of Amtrak. What we need here is we only need the road names. So if you recall from the first step is the trip-based correction. For each of the trip, so we are basically getting all the corrected GPS data. So then during the second step, we are basically breaking each trip into different road segments by each road and the different road. So the third part is a kind of like a little bit thinking part, is that calculating the overlap road segments. So for example, you see from the figure here, basically the black route from A, C, D is the recommended route, for example, is what is the app showing to the participant. However, the B, C, D route is actually driven by a real participant. So we can see there is an overlap from C to D point. However, there is the part beyond from B to C is not consistent with the recommended route. So what we did is basically we are projecting for each of the two routes, the recommended routes as well as the real driving routes. We project their longitudinal information as well as latitude information. So basically, you will create a maximum value of the longitudinal information, minimum information about longitudinal value. You also created a maximum latitude value as well as the minimum latitude information. So you just created a space of a two-dimensional space. So then you calculate. So for the real driving route B, C, D, you do the same thing. So then basically of all these two sets of data, you just calculate within these not circle, this is the two-dimensional rectangle, what is the overlapping points that they all within this rectangle you created by using the algorithm I was just talking about. So then basically is the C to D routes, it qualifies it. So that is exactly our calculation. What is the overlapping part of our real driving when you consider the recommended routes? So that is how we calculate the percentage of the distance that people really having the same driving routes as the recommended route. So that is the GPS data introduction. So then what we did is that we have two types of output data. One is a binary, yes, I followed, no, I did not follow. The second is what percent yes you followed, what is the percentage that participants follow the recommended routes. So then the followed step is the analysis part, that we actually employed two types of analysis. One is called a mixed model analysis. The second one is called a multi-label random forest tree method. So for the mixed model analysis, because it's we had repeated measurements from each driver. They had repeated trips information. We have both random effects as well as fixed effects. For those fixed effects, including their age, their gender, as well as their trip purposes. We also have the random effect of the participants themselves, as well as interactions between them. So we use the mixed model analysis to identify what kind of factors affecting people making the choices. So then, if you recall, the next step is that for this particular study, we found there is a multi-label issue. For example, the three recommended routes, they are not mutually exclusive. They can be, the route one can be the fastest one. It also can be the equal routing one. So then what we did is that we employed the multi-label random forest technology to model, predict the driver's choices, route choices for this situation. So here's some results coming from our phase 1 analysis. So the first one is modeling drivers' route choices. As we mentioned, the driver's route choice is a multi-label problem, since each recommended route may have several different features at the same time. So we actually did the analysis separately. For example, for this one is the fastest route. If given a fastest route, that drivers more likely to choose the faster routes, which has the highest average probability, which is about 83.4%. So then the second one is the equal routing choice, that if given equal routing choices, people that 78.6% of the time, they will select it. While the third one, which is the balanced one, has the lowest selection rate, which is about 71%. So then here's some results from the mixed model analysis. So the dependent variable is whether the drivers will choose the equal routing choice or not. That is our main interest, right? So then we have a set of independent variables, including route information. For example, the distance, distance saving, average gas consumption, recommendation sequence is whether these specific equal routing choice is presented as the first route or the second or the third, and also number of routes available. We also have the information, driver characteristics information, age and gender. We also have their survey data in terms of trip purpose, decision time, household passenger, how many of them, and the non-household passenger, how many of them. We also have whether it is flexible for them to basically get there a little bit later, also some kind of prior activity and leave earlier information. So one thing I want to mention that we also, because we have collected that information about the trip purposes, which is presented here in the pink in the pink shape here. So you see most of the trips were related to going back to home or going to work or shopping. We also found the information from the National Household Travel Survey about driving purposes. We actually find that these data, our data, actually are very consistent with the data that are on the national base, that the first the main trip purposes is going home, followed by work or school, then shopping, then social, then picking up or dropping off, then going to restaurant and others. So this is kind of give us like a confirmation that our data actually represent the national trends in terms of what people have completed or input in the survey. So the mixed model analysis is showing, the results is showing here. So we generally found that drivers were more likely to select the eco route when its distance was shorter and the gas consumption per mile was higher. So people are selecting the eco routing choice based on some preconditions, and also giving the priority to recommend the eco route could guide the drivers to choose the exactly the recommended way. So that means that if I give the first presented, if the eco routing choice was the first route when presented, so drivers are more likely to select it. That is also interesting to know. So here's the results from the multi-label random forest classification model that we predict the driver's route choice behavior. So we are interested in knowing that we have about 14 independent variables. So we are interested whether the drivers are going to pick eco routing or the fast one or the balanced one. So it's a multi-categorical output data there. So total sample we have is 737 trips data. So the training versus the data ratio for the training versus testing is 7:3. So we actually had a pretty good the accuracy of the model results, that for the training accuracy is about 87%, while the testing accuracy is about 79.3%, almost 80%. So we also used other algorithms, for example, K-neighbors, classifiers for vector machine. We so far found that the multi-label random forest gave us the best results so far. So the finding here is basically we found that variables from the route information showing the largest impacts. So if you see the figure, the bottom figure here, from up to bottom, that means the so the x-axis is the relative importance of that particular variable in the prediction model. So the most important variable that we found from the data is the distance saving. Then the second one is a sequence, which means that it's the first presented as the first route, or the second, or the last one. The total distance of the trip, then followed by average gas consumption, number of routes available, prior activity, purpose. Interestingly, we find that from these set of data, the age and gender were not really showing significant effects up there. So next is basically we know that people like to pick the fastest route most likely, and so next question we are interested to answer is that once people pick that recommended route, will they follow it in the real life, right? So then we actually try to answer the question whether they following the recommended route, what kind of factors and variables are impacting that. So we found, interestingly, the average probability that drivers would actually follow the route after they choose from the recommended options was not that high. It's only 56.7%. So that's basically, on the other hand, is basically to tell you that human information processing, human decision is a complicated system. Even people said that, okay, I'm gonna pick this route, but it's only 57% of the time they will follow it. But when you look at all the three route choices, eco routing, fastest route, as well as the balanced one, we found that basically for the eco routing choice and the fastest choice, actually people are more likely to follow if they pick them when compared to the balanced route choices. So for these, we also did the mixed model. The dependent variable is basically whether driver following the selected route. That we have a set of 12 independent variables, including route information, driver characteristics, as well as what the data information coming from the survey data. So generally, we found that if a driver choose the eco or fast routes, they are more likely to fully drive along the recommended route when compared to the balanced one. Compared with driving alone or with only one household passenger, drivers will more likely to comply with the recommended route when there are 3 or more household passengers. So that's basically the results of our phase 1 analysis. So the conclusion here is that our study basically showed the consistency in terms of the trip purposes with the national household survey data. We also found that drivers were more likely to select the eco routing choice when its distance was shorter and the gas consumption per mileage was higher. And if given the priority to recommend the eco routing choice, which is basically to say, just having the eco routing choice always as the #1 route, then people are more likely to select it. Then once the driver choose the eco routing choice or fastest routes, so they are more likely to follow the recommended route. So that is, so compare again, so also we found that in terms of the number of passengers in the vehicle, we also found some effects up there. So currently we have a working manuscript, is under development. So this is, so what I talked here today is basically our phase 1 analysis. So the phase 2 analysis is basically we are looking at, we know because for all the participants in this specific study, they were participating in the AACVT data. So we actually have a lot of baseline driving data from each of the participants. That means that we know we have all the driving data that collected from the ACVT study, that they do not have these eco routing navigation system. Before they had this navigation system, we know exactly what their driving routes are, everyday trip life. So there our phase 2 analysis purpose, we are compare the baseline driving that before they had the navigation system. We're going to compare that data with their driving data that from these navigation study data. So that's the baseline versus treatment. So then basically we can generate a driver's route choice decision model in a more complicated way. So with that, here's the reference of what we talked about today. And I want to basically thank our CCAT Center for sponsoring this study. This is a very interesting study. And I also want to thank Department of Energy for providing a partial, as well as the National Lab for providing the partial of the funding as well. So with that, I would open the floor for questions.
This is from Honda. The first one, did the participant clearly understood shortest distance can be different than shortest travel time? I often have found the relations.
Oh, yes, exactly. Because for the trip, each of the route information, we have three segments. One is the fuel consumption. One is the total traveling time. One is the total distance. So they understand those are the different things we are evaluating here.
So all of these, the distance and time are being given to the participants.
Yeah. Exactly, prior to each trip.
Yeah, so there's a follow-up question on that, and drivers often think shortest distance means shortest travel time, but I think you answered the question. These are being given to the participant.
Yeah, exactly.
Okay, so there's another question. This is from Trey. Very interesting work, and many questions were explored. The compliance of route following was almost the same for the 3 tabs. Why do you think drivers were not complying? Do you think they were often minor route changes by the driver, or were they going very different routes?
That's a very good question. We also asked ourselves why is that, because there are some potential reasons. First of all those participants are like residents of this neighborhood for many years. They already know the way and routes very well. They were very familiar. For example, if I going from my home to my working place, probably I would just follow the route I have traveled like many times, 100,000 times already before I have the navigation system. So that is one of the potential reasons that why people are not complying with the recommended route. So basically, familiarity is that people still stick with the most familiar route they are aware of. And also, we believe that by comparing the baseline driving data with this treatment data, we will dig out more information to answer that question as well.
Okay, and there's another question. They're asking any sense for how real or accurate for the fuel consumption estimate are?
That's a very good question. To be honest with you, because this part was not conducted by our team, but conducted by Oregon Lab. But I know they are the experts in this domain, so I would respect their expertise and trust their equations. So we did not really check the validity or accuracy of the calculation for this sense. However, we do think that they are the experts on this topic, so they should be pretty accurate. And also, like, regardless of the accuracy of those provided data values in the recommended routes, I would say it's not really about whether that's 99% accurate or let's say 80% accurate. It's just basically to evaluate once driver provided all these three options. One is the shortest one is the most fuel consumption efficient, the other one is somehow between them, which one they're gonna pick.
So they actually have a follow-up question is, in your example, and it looks like in the example, the lowest fuel route, which is, I think it's route 1, is exactly the same as the lowest time.
Exactly. That's what I said, because for this one, for this study, we have found out each route is not mutually exclusive. They can be, they can have for each recommended route, it can be multi-labeled. For example, for the route 1, it can be labeled as the most fuel consumption efficient. It also can be the fastest one.
Yeah, and the same from the same people who asked this question. How often does this happen, and how do you classify this?
So very good question. I don't have the percentage of how does this, how often does this happen, but we do have that data. So if you're interested in data, I can check that. I can share with you. We do check at that. So how we handle this situation is that in the analysis, if you recall, we use the multi-labeled random forest classification algorithm, which that for each given route, for example, for this example, the route 1 will have 2 labels. One is the eco routing one. The second one will be fastest one.
Okay, Shan, since we're on this topic, if you can move to the next slide, I actually have a
this one?
The next one. Yeah, the calculation of this fuel consumption. It looks like the calculation is utilizing average speed and and the indicator in terms of whether it's a city or highway. Since you have detailed route and you also have sort of the GPS, you also have sort of in terms of stops and speed at each point. It looks like you have more information you can leverage to calculate this in a more accurate way.
Yes, absolutely. We can, but again, the purpose is not about how accurate of the for each given recommended route, whether the estimate time or estimate fuel consumption. How we can calculate that information on the background, but I think for the purpose of to see how drivers gonna follow or select each of the route based on giving provided information, I think may not be that critical. I could be wrong, but I do think that the whole idea of this study is that by giving you this information based on the estimation we have here, we have the shortest one, we have the most fuel consumption efficient one, we have someone in between, which one you're gonna pick.
Yeah, but I would think this is actually quite important, because if the information is accurate, then people may have more confidence in it, and so that they can make informed decision on those. But this part is probably done by Argonne, right?
Right. Yeah.
Okay. Yeah.
But you did bring out a very important component that is about users' trust, that we did not really evaluate that in this particular study, but it will be very interesting that we should include that piece in the future studies.
Okay, thank you. There's two more questions in the chat box. I will just, since we have maybe 1 or 2 questions, 2 minutes. And there's a follow-up question again on the eco route. And how do you classify as an eco route?
Oh, basically the eco route is just, for example, it's just basically the most fuel consumption efficient. Let me just go to that slide, which has the lowest MPG. Which route has the lowest MPG value is classified as the eco routing one. That is the based on the definition.
Okay. Another follow-up question. What do you think can help increase utilization of the recommendations by the system? So basically, yeah, encourage the user to use the recommendation more often.
Yes, that's a very good question. I would say that is a very typical human factor study. Well, we know that human decisions are complicated. There are many factors that impacting their when they are making decisions. So from what I can recommend is basically, first of all, our results show that every time if you present the eco routing choice as a number 1, they are more likely to select it. And also we found that sometimes people just very stick with their the old routes, the route that they are familiar with. So we have to give them a period from time to time, like a feedback system. For example, I also proposed this idea to DOE as well, because we have found that providing feedback system can actually helping people to generate new habit. For example, like by end of each month, you can present it to the driver. Hey, by selecting the eco routing choices, for example, you have made 100 trips for this April or May. Out of the 100 trips, you actually you picked the eco routing choices 50% of the time. By doing so, you have saved, let's say, 10 gallons of gas, and basically that will save you, let's say, $10, for example. By giving people very direct consequences, and also you have the enforcement from time to time, people will generally starting to adapt to the idea and starting a new driving habit.
Very good. Thank you, Dr. Bao. And I think we are running out of time. Thank you, everyone, for joining us for this edition of our CCAT Research Review. We will be hosting another research review in early July. And I hope you follow us on Twitter and LinkedIn, and so that you can get the registration details. Again, thank you very much. Have a good evening.
Thank you, everybody.
Thank you. Bye-bye.
Bye.